Okay, it's 5:30, so let's go ahead and get started today. All right, good afternoon, everybody. How's everyone doing today? Doing good, hope? Good, good. All right. So today the plan is we're going to continue on with our lecture notes on unsteady problems for finite volumes. So for those of you who are doing the project with finite volumes, either you're a grad student or you chose to do so, this is going to be important to you. So because we kind of had to put this in at the end, we're not going to be able to get a homework assignment on this. So the last homework that I have right now is on a higher order method. So this lecture and probably the next one too is mostly for those of you who are doing the project with finite volumes. Okay, so a couple announcements before I begin. So speaking of the final project, so I got the rubrics up for you guys on titanium, so that should be on kind of the final week there. And I've included kind of 3 separate things that you need to turn in. So I made an assignment to turn in your final report. I made an assignment to turn in your code. And I also made an assignment to turn in the videos, because those are kind of the 3 deliverables that I wanted you to turn in for the project. Okay? And just like we talked about on Monday, the final project is going to be due, everything's going to be due on Monday, May 18th. So that's 2 weeks from the following Monday. So next week is our last week of class. The following week is finals week. And then that last week I have to submit grades. So I'm going to have it due that Monday, just so I have enough time to grade everything. Okay. So that's there for you guys. The other announcement I want to make is that I think maybe you guys got this email already, but the SOQs for this semester are going to be done online. So normally we do this the course evaluations in class, but since we don't have class anymore, they've moved it online. So please fill that out. So everyone kind of views those evaluations a bit differently, but for me, because I'm still relatively new at teaching. I'm looking to kind of improve as much as I can, and kind of a big piece of that is hearing from you guys, your honest opinions about what works and what doesn't. So I really want you guys to fill that out. Please take your time, and please be honest about everything that worked well and didn't work well. And I know, especially for this class, I've made a lot of mistakes, and we've kind of had to adjust a lot of things on the fly. So hearing from you guys about what were some of the pain points and what were things that could have been done better is really going to be helpful for me, as I move forward, to teach this class again, and also a lot of my other classes. Okay. So make sure you fill that out. What I heard was that they're going to give you a really annoying kind of message every time you log into the portal. So kind of the sooner you get that done, kind of the better. Okay. Okay. So are there any questions about that or the project or anything before we begin today? Okay. So let's go ahead and get started. So let's pick up where we left off last time. So I think for the last 15 minutes on Monday, we started the lecture notes on unsteady finite volume problems. So let's kind of continue that. So I think we were doing an example. Okay. Right, so the example was we had d phi dt is equal to 3 d squared phi dx squared. Okay. And then what I wanted you to do was to solve this with finite volumes. Okay. And then since we have an unsteady problem, we also need a scheme to march this equation forward in time. And so to do that, we're going to use the explicit Euler method. Okay. And then just for completeness, let's write out the boundary conditions. Okay. So the boundary conditions, first on the left-hand side, we have a Dirichlet condition. So we have phi of x is equal to 0 is equal to cosine of pi t. Okay. And then 2, we have d phi dx at x is equal to 1 is equal to cosine pi t divided by 2. Okay. And then since it's an unsteady problem, we also need an initial condition. So our initial condition in this case, we're going to assume everything starts at 0. Okay. All right. So I think where we left off was where we were just about to write out kind of the general form of the equation. So after we apply finite volumes to the whole equation, we're left with this equation here. So we have phi c at n plus 1 minus, minus phi c at n, all divided by delta t times delta x is equal to k over delta x times phi r minus 2 phi c plus phi l. Okay. Where the term on the right, that results from doing a finite volume discretization of the diffusion term, and then the term on the left, that's our finite difference equation for the time derivative, plus this delta x. Well, remember, this delta x comes from our trapezoidal rule. Okay. Because remember, when we integrate d phi dt dx, what we get is d phi dt times delta x at c. Okay. Okay. So now that we have this this equation here, where we've already discretized the space, now we need to start applying our explicit Euler. Okay. And remember, to apply an explicit time advancement scheme, we take all of the phi terms that don't have a time index, which are all of these guys, okay, all of the phi terms on the right-hand side, and we're going to apply a time index of n. Okay. So let's put n, and let's put n right there. Okay. And so now that we've done that, we're done kind of applying methods to this equation. So all we need to do now is we need to just rearrange it algebraically so that we get an expression for phi c at n plus 1. Okay. All right, any questions on this before I turn the page? Okay. So let's go ahead and do that. So remember, whenever we're doing an unsteady problem, the way we arrange the equations, we have all the terms with n plus 1. We put those on the left-hand side. And then on the right-hand side of the equation, we put all the phi terms that are evaluated at n, plus all of the known. So those are things like the source terms and all the boundary conditions end up on the right. Okay. So then if we do that, we end up with this. So we get phi c at n plus 1. Okay. Since we only have just that one, because it's an explicit equation. Okay. Then we get phi c at n plus k delta t divided by delta x times delta x squared, sorry, phi r at n minus 2 phi sub c at n plus phi l at n. Okay. So what I did from the previous equation is I multiplied both sides by delta t to eliminate that from the left-hand side, and I also divided by delta x. So that's why we have a delta x squared. Because remember, we had the delta x on the left-hand side from the trapezoidal term, or trapezoidal rule. And so now let's take this equation, so we're almost done, and let's rearrange it so that we get coefficients for each of the phi terms. Okay. Just so it'll be easy to kind of plug and chug once we get to that. So we get phi sub c at n plus 1 is equal to k delta t divided by delta x squared times phi r at n minus, or say plus 1 minus 2k delta t divided by delta x squared phi sub c to the n plus k delta t divided by delta x squared phi l to the n. Okay. And so for this problem, which is just simply an unsteady diffusion problem, so we have no convection here, this is our time advancement equation. And so just like always, this equation is going to be valid for all of the interior cells. So in this case, we have 5 finite element cells. So I think I forgot to mention that today, but last time we mentioned that. So we can apply this for cells 2, 3, and 4, because 1 and 5 we need to apply some boundary conditions. Okay, so if we plug in the numbers, so let me just do cell number 2, then we get the following equation. So we get phi 2 at n plus 1 is equal to, let's see, 0.075 plus, or phi 1 to the n plus, plus 0.85 phi 2 to the n, okay, plus 0.075 phi 3 to the n. And then you can also plug this in for cells 3 and cells 4. Okay, so notice for cell 2, our left neighbor is cell 1, and our right neighbor is cell 3. Okay? So I kind of swapped it here. So up top here, I had the right one first and the left one second, but you can interchange them just because they're algebraic expressions. Okay? All right, any questions on this for all of our interior cells? Okay. So now let's do the boundary conditions. Okay. So let's start on the left-hand side. So let's on the left-hand side, we know we have a Dirichlet boundary condition on cell 1. Okay. And so we know that for Dirichlet boundary conditions, we need to modify our equation. Okay. So in particular, for the first cell, when we're evaluating our diffusion term, our diffusion term has this derivative. Right. So when we do the finite volume approximation for diffusion problems, we know that we have the diffusion term on the left face and one on the right face. So since our Dirichlet condition is on the left, it's going to modify our derivative on the left side. Okay. So this is going to be phi c minus phi naught, or phi naught in this case is going to be a function of t, because remember phi naught was cosine of pi t. And then we're going to divide by delta x over 2. Okay. So if we plug in for phi naught of t, which is our Dirichlet condition, we get 2 over delta x times phi sub c minus cosine pi t. Okay. So this was our Dirichlet condition. And this was given to us in the problem. Okay. And so just like we did with all of our steady problems, now that we have this expression for d phi dx at the left side, let's go ahead and plug it in. Okay. Because our original equation looked like this. So we had phi c at n plus 1 minus phi c at n, all divided by delta t times delta x is equal to k goes on the outside here, k d phi dx at the right side minus d phi dx at the left side. Okay. And so let's take this expression here and plug that in for that. And then for the right derivative, we can just use the same expression as before because we have a neighbor on the right-hand side. Okay. So then this gives us phi c at n plus 1 minus phi c at n all divided by delta t times delta x is equal to k phi r minus phi c divided by delta x minus 2 over delta x phi c minus cosine pi t. Okay. And then from here we can simply just rearrange the terms, and we know that phi sub c is going to be phi 1, because remember this is going to be for cell 1 right here. Okay. And then once we do that, we end up with the following expression. So we get phi 1 at n plus 1 is equal to k delta t over delta x squared times phi 2 at n. Make this a little bit neater. Okay. Plus 1 minus 3k delta t all over delta x squared phi 1 at n. Okay. Plus 2k delta t all over delta x squared cosine of pi t. Okay. And this is our algebraic expression for cell 1, which we can add along with all the other ones. All right. Any questions on Dirichlet boundary conditions? Okay. So that's the Dirichlet condition on the left side. So now let's do the Neumann condition on the right. Okay. And so our Neumann condition on cell 5, so we know that the Neumann condition is going to be bordering the right side of cell 5. And so what we're going to do is we're going to replace this entire derivative. Okay. So remember, when we're doing Neumann conditions in finite volumes, we just kind of replace the entire derivative term. So that's going to be phi of, or gamma of t, okay, which in this case, gamma of t is cosine of pi t divided by 2. Okay. So then if we factor that into our finite volume equation, we get the following. So we get phi sub c at n plus 1 minus phi c at n, okay, all over delta t times delta x, okay, is equal to k. We're going to plug in this guy for d phi dx at the right hand side. So we have cosine of pi t divided by 2 minus phi sub c minus phi sub l all divided by delta x. Okay. Okay. So then if we rearrange the terms and we solve for phi c at n plus 1, then we get the following. We get phi, and since we know this is for cell 5, so we'll plug in phi 5 for phi sub c. This is phi 5 at n plus 1 is equal to k delta t divided by delta x squared times phi 4 at n, okay, plus 1 minus k delta t divided by delta x squared phi 5 at n plus k delta t over delta x squared cosine of pi t divided by 2. Okay. So there's our algebraic equation for cell 5. Okay. So now that we have the two boundary cells and we have all the equations for all the interior cells, that makes up our algebraic equations. Okay? So we can basically just plug in numbers for this and then evaluate all those coefficients. Okay. Any questions on the Neumann boundary condition? Okay. So before we jump into the MATLAB code, I just want to show you what these equations look like in matrix form. Okay. So in matrix form, they look like this. So since we have 5 cells, we're going to need a vector that's 5 deep. So we have phi1, phi2, phi3, phi4, phi5, okay, at n plus 1. Okay. And this is equal to our matrix of coefficients. So if you plug in all the numbers, you end up with the following. So you get 0.775, 0.075, and then 0, 0, 0. Okay. Then we get 0.075, 0.85, 0.075, 0, 0. Okay. Same thing here. Okay. And then one more row of this. And then we have our final row, which is influenced by the Neumann boundary condition. Okay. And so multiplying this will be our solution vector at n. Okay. But remember, all of these solution values at n are going to be known, because that's the solution at the current time step. So either we're using our initial condition or we're using our solution that we computed at the previous time step. Okay. So just like we always have, we have a structure on everything on the left-hand side we don't know yet, and we're using all the things that we do know on the right-hand side. Okay, so that's the matrix form of the equations. Any questions on this before we jump into MATLAB? Okay. Share my screen. Okay, so this is the unsteady diffusion code with finite volumes that I posted on Titanium. So this is the 1D code, right? So let's see here. So section 1 here is going to be the same as before. So here we define the length of our domain, the number of finite element cells that we have, the grid spacing, the diffusion coefficient, the time step size, and all of this good stuff. Okay. So here I'm also making a video of this. So I'm going to write the video file, and that's what this code does. And then just like for any unsteady problems, so if you kind of think back to when we did unsteady problems for finite difference, before we begin, we need to kind of initialize our solution at the next time step and the solution at the current time step. Okay. So remember, these variables represent the solution at n plus 1. Okay. And then sol cur, this is our solution at time step n. Okay. So we initialize both of them to 0. Remember, our initial conditions were 0 everywhere. Okay. Okay. So let's jump into the time stepping loop, because remember, this is an unsteady problem. So whenever you have an unsteady problem, you always have your time stepping loop. As most of you have probably seen from the project already. Right? And then inside the loop, we have to define our matrix of coefficients. So that's what this is doing here. So basically, the matrix that I just showed you just now, we're building that up using a for loop here. Okay? So we're visiting every row in the matrix, or in this case, visiting all the interior cells. And then we're setting the rows of the matrix to be like that. Okay? And then meanwhile, we're also setting the first row and the last row, because these rows depend on the boundary conditions. So first we have the first row that corresponds to the Dirichlet boundary. So you should see that these coefficients here correspond to what we derived in class. So for A11, this is the coefficient for phi sub c. Okay, we have 1 minus 3k delta t divided by delta x squared, and then A at 1, 2. So this is phi at right, okay, our right neighbor, because this is our Dirichlet condition at the first cell. Then we have k delta t over delta x squared, and then b, which is the forcing vector. We're adding up our Dirichlet boundary. Okay. And then you come down here. This is the same thing for the Neumann condition. So Neumann condition, we have a n comma n. So this is phi at c. And then phi at n comma n minus 1, this is phi at L. Okay. So this is our left neighbor. Okay. So then once we have our left-hand side matrix and our vector defined, then we can go ahead and advance this forward in time. And so to do that, we simply take our left-hand side matrix, multiply it by a current solution, which is what we saw previously, and then we add to that any additional forcing from the boundary conditions, which is our vector B. And then after that, we save the current solution, and then we plot it. So I think probably you guys can't see this, but I'll run it anyway. So if you run this code yourself, what you should see is a string that looks like it's kind of wiggling up and down. Oh, you can see it. Okay, great. Yeah, so it's going really slowly, but you can see the string going up and down right there. Okay, and the reason it's vibrating is because we have the boundary conditions that change with time. Okay, so any questions on this MATLAB code? So remember, for unsteady problems, we're following kind of the same methodology that we always did, which is, first we work on the spatial derivatives. So we use our typical finite volume scheme where we integrate, we apply divergence theorem, and then we apply the trapezoidal rule. Just the only thing we do is we kind of add this kind of extra term over there, and that kind of modifies our equations a little bit. But up until the point where you have to apply the time derivative, all of it's kind of the same methods as we did before. That's kind of what I want to emphasize to you guys. Okay, any questions on this while this is still kind of giving us the wave here? Okay. So let me bring back the notes. Okay. Okay, so the notes are back. Okay, so that was explicit time integration. So explicit, remember, is a good method if you are not really worried about stability, because it's even though it's per time step, it's cheaper because we're not solving any system of equations. Most of the time, you run the risk of instability. So actually, for a lot of practical problems, implicit time advancement is usually the way to go, because then with implicit time advancement, then you know for sure that your solution is going to be stable. Okay. So let's see how we do implicit time marching for finite volume problems. Okay. So just so it's relevant for your for the projects, because for the project I implemented a implicit method for you. Okay? So I'm going to do basically kind of the most general kind of problem that we can do. So I'm going to do an implicit time marching for finite volume problems in 2D. Okay, with both convection and diffusion. So in the previous example, we just had diffusion. But in this example, I'm going to, or for everything that we're going to do for today, I'm going to assume that we have both convection and diffusion. Okay. So let's write out our general equation. Okay. So in 2D, our general equation might look like this. So we have our unsteady term. Next, we have our convective term. Then we have our diffusion term. Okay. And then on the right-hand side, we have our source. Okay. So this is kind of the most general form of the equation which we have. So on the time derivative term is obviously our unsteady term. This is our convection term. This here is our diffusion term. Okay. And here's our source. Okay. And so just like we typically do for finite volume problems, our first step is going to be to integrate this entire guy. We're going to integrate it over the region of a single cell. Okay. So that so in 2D that means double integrals all around. Okay. Okay. So if we do that, we get double integral of d phi dt dA, okay, plus double integral. And since the convection diffusion terms, we always take those together. I'll kind of lump them into the same integral, because okay, we're going to apply divergence theorem on both of them. So we have delta or nabla times v minus k nabla v, okay, just like that. And then this is equal to our source term. Okay. And so just like we typically do, for all of these guys, since they're a double integral with a nabla, what we're going to do is we're going to apply divergence theorem. Okay. And then for the time derivative and also for the source, we're just going to straight up apply trapezoidal rule and evaluate these epicentroid. So since this is kind of the final topic in the class, I thought we kind of go through it all kind of from scratch, just so we kind of remember the whole process that we took to get here. All right, any questions on this before I turn the page?
So you said the time integral is going to be through trapezoidal rule?
Yes. Yeah.
Okay.
Yeah. So we're basically just going to multiply it by delta x times delta y, and then just evaluate it at the centroid, so phi sub c.
Okay. Thank you.
Mm-hmm. Okay. So let's go ahead and turn the page. So let's go ahead and do all those things. So first thing is the trapezoidal rule for the time derivative. So we have d phi dt. Okay. And since we apply trapezoidal rule, we're applying it at the centroid. So that's d phi sub c dt. Okay. And then from there, we multiply it by the area of our cell. So the area of our cell is going to be delta x times delta y. Okay. Next, we applied our divergence theorem. So it's going to transform that double integral into a line integral. So then this becomes phi v dot n minus k del phi dot n, okay, ds, right, is equal to q at xc yc times delta x delta y. Okay. And so, because remember, we're doing this over our square cell, where the length is delta x and the height is delta y. Okay. So delta x times delta y is literally just the area of our cell. Okay. And so just like we saw with the kind of the previous two units, when we have this line integral and we're doing it across the boundary of the cell, okay, that's going to split this line integral into 4 separate ones, each for each side of the face. Okay. For north, south, east, and west. Okay. And then since we also know the normal vectors on each of these faces, okay, remember that that normal vector will affect you know, which terms we retain once we take these dot products right here. Okay. So then if we do all that, then we're left with the following. So we get d dc dt, okay, times delta x delta y. Okay. Now we're going to add in our integrals, or each of our 4 different integrals. So first we're going to do the east integral. So our east integral is going to be phi u minus k d phi dx, okay, dy, plus integral on the north face. Let me do that on the next line. We're going to run out of space. Of phi times v minus k d phi dy, okay, and that's dx, minus integral on the west face. So that's going to be phi times u minus k d phi dx dy, minus our integral on the south face. So that's phi v minus k d phi dx times dx. Sorry, it should be dy right here. Oops. And all this is equal to q at xc yc delta x delta y. Okay. So when you kind of write it all out together like this, it ends up being pretty long. Okay. And so the next step is we're going to take each of the integrals on the face, all the faces, the east, north, west, and south integrals, and we're going to apply trapezoidal rule. Okay. Because eventually, remember, we want to get an algebraic expression for everything here. Okay. All right. Any questions on this? Okay. So the next step is apply trapezoidal rule for all the face integrals. Okay. And so if we do that, we get the following. We get d phi dt. Okay. So our time derivative term, we haven't done anything for it yet. Okay. The only thing we know is that we're applying it at the centroid. So that's delta x, delta y, okay, plus phi little e times u minus k d phi dx at the east face, okay, delta y plus phi little n times v minus k d phi dy. This is at the north face, okay, delta x minus phi little w u minus k d phi dx, and this is at the west face, delta y minus phi little s v minus k d phi dy at the south face, delta x. Okay. And that's equal to q of xc yc delta x delta y. Okay, and so the next step is to take all of the phi values at the little letters, okay, and put those in terms of the cell-centered values. Okay, so remember we use the little letters to represent the quantities at the faces of our cell. But what we want is we want to put everything in terms of the cell-centered values. Okay. All right. Any questions on this? Okay. Okay. So we have we have two kinds of substitutions that we need to make here. So we have our convective substitutions. Okay. So for our convective substitutions, we have simply just the solution value at the face. Okay. So for instance, we have phi little e. Okay. So remember, there's several ways that we can do this. So we can either do just a basic central scheme, where we just take the average between the phi sub c and the east neighbor. Okay. Or we can do an upwinting scheme depending on the direction of the velocity. Or we can do a quick scheme, which is what we did, what we learned when we did higher order schemes on Monday. Okay? But just kind of for the sake of simplicity, I'm just going to assume just a basic central scheme. Okay, so for the value at the face is just going to be simply the average of the cell-centered value of yourself and the neighbor that it also touches. Okay, so if in this case we have phi sub little e, okay, this is going to be the average of phi sub big E, which is our east neighbor, and phi sub c. And so for the diffusion terms, we're approximating the value of the derivative at the face. Okay? So you have d phi dx at the east face. Okay, and remember we're going to assume our basic linear profile, and then this value here is just going to be the slope of that line. Okay, so this is going to be phi sub e minus phi sub c, all divided by delta x. And then since we're going to be plugging in for all these guys, let's go ahead and plug in our time derivative. Okay. So our time derivative, we're going to use our same finite difference. We're going to have phi sub c at n plus 1 minus phi sub c at n, all divided by delta t. Okay. So basically, everywhere I see a derivative of phi or or a face value of phi, I'm going to plug in something like all of these. Okay. Okay. And then we're going to end up with the following expression, which is going to be very long. So we have phi sub c at n plus 1 minus phi sub c at n, all divided by delta t, delta x, delta y. Okay. Now let's do another thing too. Let's assume that our delta x and delta y are the same and that they're just going to be delta, just to kind of save us a little bit of room. Okay. So delta x, delta y is just going to be delta squared. Okay, and this is going to be not equal to. We're going to add. Okay. First thing we're going to add is our east integral. Okay. So our east integral is going to be u, and then we're going to plug in the our convective term up here. So there's phi sub e plus phi sub c, okay, all divided by 2 minus k phi sub e minus phi sub c, all divided by delta. Okay. And all this is multiplied by delta. Okay. Plus, then we have the expression for the north integral. So this is going to be v phi sub big N plus phi sub c, all divided by 2 minus k phi sub big N minus phi sub c, all divided by delta. Okay. And then this quantity here is going to be multiplied by delta. Okay. Minus u, this is going to be our west integral. So this is phi sub big W plus phi sub c, all divided by 2. Okay. Minus k phi sub c minus phi sub W, all divided by delta. Okay. And that's going to be multiplied by a delta as well. Okay. And then finally, we have our south integral. So our south integral is going to be minus v times phi sub s plus phi sub c, all divided by 2, okay, minus k phi sub c minus phi sub s, all divided by delta, okay, times delta. And this is equal to q of xc yc delta squared. So it's a lot of terms because it's a 2D problem, and we're basically doing it as general as we can. Okay? But what I'm going to show on the next page is kind of just the general formula after you kind of rearrange all these terms that you can apply. All right. Any questions on this? Okay. Okay. So before I show you the general equation, we have to make sure we do one more step. Because remember, this section was based on implicit time advancement. So we know that for implicit terms, what we're going to do is for every phi term that doesn't have a time index, we're going to give it a time index of n plus 1. Okay? Okay. So basically, all the phi terms that result from the convection and diffusion terms, we're going to give them an n plus 1. And then once we do that, we're going to put it in the same form as we did for the explicit term. Okay? So we're going to have everything with an n plus 1. We're going to keep that on the left-hand side of the equation. And then everything with an n, we're going to put it on the right. Okay? And then we're going to add any additional term. So that additional term will come from mostly the source term. Okay, so let's go ahead and start writing it out. So since it's an implicit solution, we have a lot more terms with n plus 1. So our left-hand side is going to be pretty filled. Okay. So we have u delta t all divided by 2 delta, okay, minus k delta t all over delta squared. And this is our east neighbor at n plus 1, okay, plus v delta t all divided by 2 delta minus k delta t all over delta squared v n at n plus 1, okay, plus minus u delta t all divided by 2 delta minus k delta t all over delta squared, and that's vw at n plus 1, okay, plus minus v delta t all divided by 2 delta minus k delta t all over delta squared, and this is vs at n plus 1, okay, plus 1 plus 4k delta t all over delta squared, b sub c at n plus 1 is equal to q at xc yc delta t plus phi sub c at n. Okay. So it's a lot of terms, it's a lot of coefficient, but this is kind of as general as you can get, okay? So basically kind of any problem that has convection and diffusion in 2D, and you want to advance it with implicit Euler, this is kind of your master equation here, where you can kind of just plug in for all the parameters, okay? So this is for implicit time advancement for 2D convection with finite volumes. Okay. Okay. Any questions on how we got here? So for those of you guys who are using finite volumes for the final project, and I ask you to basically implement a basic, central scheme to do the time advancement, this is basically going to be your master equation right here. So, a lot of the places where I say insert here for a coefficient, you're going to use kind of expressions from this formula here. But, as I was kind of telling other people, so when you do implement higher order schemes, you're going to need to kind of do a similar derivation that we did just now. So we did kind of higher order schemes for steady problems, and now we're doing an unsteady problem with kind of the basic central scheme. And so in order to get the coefficients for the quick scheme for an unsteady problem, you kind of have to work through kind of a paper, a hand calculation like this, just so you get the correct expressions for the coefficients. Okay? So I've, just to kind of help you out with that, because I know that's kind of a lot of work, I've given you the solution for the east integral, and that's with kind of the basic scheme and the quick scheme, just so you can have that as reference. Okay, so there's no questions. Let's jump into an example. Okay. Oh, another thing, I should mention is from the last equation, since we had a bunch of terms on the left, what we're going to get is we're going to get a solution. We're going to need to solve a system of linear equations. Okay, so remember that's characteristic of all implicit schemes, where each time step is going to be more expensive because you have to solve this kind of system of equations instead of just doing kind of simple matrix multiplication and addition in order to solve your problem. Okay, so in this example, we're going to have a 2D unsteady convection diffusion. Okay. So we have d phi dt plus 50 cosine of pi t d phi dx plus sine of pi t d phi dy is equal to 3 d squared phi dx squared plus d squared phi dy squared. And then we're going to add a source term. So our source term is going to be 3xy. Okay. All right. So we have basically the whole kit caboodle here. So we have basically everything kind of at once going on. So we have an unsteady problem because we have terms with time. We have convection velocities that are going to change with time. And then we have diffusion and we have our source term. Okay. So this is kind of an example that kind of incorporates almost everything that we've done here. All right, so first thing we're going to do before we talk about the grid is let's identify the parameters of the problem. Right? So first we have u, our convection velocity. So we know that u is going to be the coefficient in front of the first derivative with respect to x. So our u in this case is going to be 50 cosine of pi t. Okay. And the next thing we'll specify is our v. Where our v is given by the coefficient in front of d phi dy. Okay? So in this case, this is equal to sine of pi t. Okay? And notice that since both of these depend on time, each of these are going to change with time. So we're going to need to reevaluate these at every time step. Okay? Okay. So that's our convection velocities. So next thing, let's identify our k. So our k is just a constant here. So k is just going to be 3. Okay. Okay. And in this problem, we also have a source term. So our source term is going to be 3xy. Okay. So now that we have all these identified, it'll be kind of easier to kind of plug in later on in the equations. Okay. Okay. So now that we've identified that, let's identify the methods we're going to use. So we're going to use a finite volume method for the space terms. Okay. And then since this was in the section for implicit time advancement, we're also going to be using an implicit Euler. Okay. Okay, so the domain looks like this. So it's our square domain. Okay. So it's a square domain with 16 cells. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. And so all around, we're going to have Dirichlet boundary conditions. So we have phi is equal to 25. On the bottom here, we have also phi is equal to 25. Up top here, we have phi is equal to 50. And then on this left side here, we also have phi is equal to 50. Okay. So we have all Dirichlet conditions all around, right? And so in addition to that, we have our time parameters. Okay. So we need to specify our time step size. which is dt, or delta t. So in this case, it's given to be 0.1. Okay. Okay. And then we also need our initial conditions. So our initial condition is we're going to assume everything starts from 0. So phi at all spatial locations x and y at t is equal to 0 is going to equal to 0. Okay. Right. All right. Any questions on the problem setup? Okay. All right. So first order of business before we get into the boundary node. So let's set the equation for all the interior cells, since we can kind of just plug into the equation that we just had previously. Okay. Okay. So we know what all of our parameters were from the previous page. So let's go ahead and plug that into that that kind of big expression right there. Okay. And since u and v are still functions of time, we're going to leave it in terms of that. Okay. So we start plugging in. We get the following. Okay. We get 10 cosine of pi t. Okay. Minus 4.8 times phi e at n plus 1, okay, plus 0.2 sine of pi t minus 4.8 and this is phi n plus 1, okay, plus minus 10 cosine of pi t minus 4.8 phi w at n plus 1, okay, plus minus 0.2 sine of pi t minus 4.8, okay. This is phi s at n plus 1 plus 20.2 phi sub c at n plus 1, right? And all this is going to be equal to 0.3 xcyc. So that's our source term, okay? Plus phi sub c at n, okay? Okay. So in order to get that, I basically just plugged in numbers into the previous equation that we had before. And so we can apply this equation directly to any cell that's on the interior, okay? Because remember, the conditions for using this equation here is that we have neighbors on all sides, because we need a neighbor on the east, the north, the south, and the west. Okay. And so for this problem, this is cell 6, 7, 10, and 11. Okay. So since our mesh was pretty small, we don't have that many interior cells. But if you're applying this for a problem with a mesh that's much more fine, you're going to have a lot more interior cells. So let me write out the equation for cell 6. So it's basically just the just that equation, but plugged in with all 6's neighbors. Okay, so for cell 6, we have 10 cosine of pi t minus 4.8 times the east neighbor. So the east neighbor for 6 is going to be phi 7 at n plus 1. Okay. Plus 0.2 sine of pi t minus 4.8 times the north neighbor for 6. So the north neighbor for 6 is going to be phi 10 at n plus 1. Okay. Plus minus 10 cosine of pi t minus 4.8 phi 5 at n plus 1. Okay. Plus minus 0.2 sine of pi t minus 4.8 times phi 2 at n plus 1 plus 20.2 times phi 6 at n plus 1, okay, is equal to 0.3 xc yc, our source term, plus phi 6 at n. Okay. So there's our algebraic equation to solve for 6. Okay, and then we need to combine this with all the other equations in order to solve for everything. Okay. Okay. Any questions on this? So we basically just did the interior cells. Okay. So now that we can basically apply the same formula to cells 7, 10, and 11, because those are all our interior cells. But then now we also need to apply the, we need to find the equation for all the boundary cells, okay? Okay. So in this case, our all of our boundary cells are actually going to be Dirichlet boundary conditions. Okay. Okay. And so remember, when we apply boundary conditions in 2D finite volumes, we need to adjust the integrals. Okay. Because remember, we have kind of our family of 4 integrals, so north, south, east, and west. The way that we apply the boundary conditions is we just make modifications to the proper integral. Okay. And so that doesn't change. So just because we're doing an unsteady problem, as we kind of saw in the derivation, we still had to, to integrate the entire thing, apply divergence theorem, and we still get our 4 integrals. It's just that, after we apply the unsteady term, just the coefficients in front kind of shift a little bit. But the process of applying the boundary conditions are going to be exactly the same. So the process is we're going to, for each cell, we need to identify which of those integrals need to be modified. And then we just make those proper modifications. Okay? So in the code, once we go over that, we'll basically, the way that we'll do is we'll do kind of the same way that we did for the higher order schemes, is we'll kind of have a block of code to evaluate each integral kind of one at a time. Okay. So it's a fair amount of work to do the boundary condition. So I think probably we'll say that for next time, because we only have about 5 more minutes. So I'm going to end a little bit early today, mostly just because next time we have a full class session and we don't have that much left of these lecture notes. And then once we're done with these lecture notes, we're basically done with the class. So I don't know if I told you guys on Monday, but my plan for next Wednesday is we're not going to cover anything new, but I thought what I'd show you guys is some of the research that I've done in the past, because we've kind of had our heads in the sand a little bit in this class, kind of doing like really heavy theoretical and code development stuff. So I kind of feel bad that that you guys haven't really seen kind of the end goal. So unfortunately, the end goal of actually developing a commercial code or a research code kind of requires a lot more work. So this is kind of, believe it or not, this is kind of only the first class and maybe a series of like 5 or 6 classes that you kind of need to take in order to develop a working code that's useful for practical applications. So I wanted to at least show you guys some of the stuff that I've done before. So so you guys don't have to do anything different. So I'll be kind of giving the lecture. I'll be giving my presentation at our normal lecture time. So if you tune in during that time, you'll get to see everything. But I think what I'll be also inviting students from some of my other classes as well. So I'm going to invite students from my graduate fluids class, which I teach after this, and also from my finite elements class. And actually, Dr. Sanders' continuum mechanics class is actually also going to be joining that lecture too. So it's going to be a lot of people, maybe, if people are interested. And then you'll kind of get to see what I've done. So I didn't want to throw anything new at you guys. We're already kind of cutting it a little bit late by finishing this lecture next week. But at least for the last class day, I wanted to at least give you guys a little bit of a break, so you guys just can kind of just listen and kind of can kind of see some cool pictures and cool animations. Okay. So if there's no more questions, I'm going to go ahead and call today's lecture a bit early. So have a great weekend, everyone. Please stay safe, stay healthy. If you have questions on the homework or the project, I'm always available through email. Or if you ever want to set up kind of a private Zoom meeting, then definitely let me know that as well, because I'm always free to meet with you guys. Okay. So see you guys on Monday. Thanks, everybody.